My name is Michael Nygard. I'm CTO of Relevance and author of the book Release It. And I'll be talking to you this afternoon about the deployment army and why we should get rid of them. What I mean by a deployment army is something like this. This is a picture that a friend of mine from a former client sent me. And what you see here is a conference room with about 40 people in the conference room. Some of them are behind the camera, some are in front of the camera. In addition to the people in the conference room, there is a Polycom phone open to a conference bridge with about an equal number of people on the phone as there are in the room. This deployment began at 4 in the afternoon. Actually, it began a little bit before that when they sent some of their people home to take naps so they could take the late shift, because this deployment will continue until 4 in the morning. Some of the notable steps during this deployment involve smoke testing by business users at 1 in the morning, where they have scripts of instructions that they're supposed to click around the site and make sure that everything's working okay. Now, of course, you can imagine that at 1 in the morning, not everyone is at their full alertness. And so some of the people executing some of the scripts report random errors that aren't actually errors, but are known conditions from years ago. Some people click incorrectly and report errors that are their own errors, not the application errors. It's a very noisy process. It involves a lot of people. In fact, they have so many people that they have steps in the plan for who to send out to get food at various points in the night. And they've added steps in the plan as time has gone by to make sure that someone empties the trash cans from all the containers from the food that they bring in to feed all of these people. This is the deployment army. It's a remarkably persistent structure. It is also an anti-pattern. It develops because of this belief, this self-fulfilling prophecy. The self-fulfilling prophecy says we have risk created by these large, infrequent releases, a certain amount of unknown code or inventory that's being deployed, and this risk produces threatening situations, threatening to the business and threatening to individuals who get blamed if things don't go well during the deployment. Their ingrained response to this ambiguous or uncertain environment is to apply people to it. And so they have this belief that the deployment army is the best way to react to unknown situations. Now, it is a self-fulfilling prophecy because humans are good at reacting to unknown or novel situations, much better than automation or scripts, in fact. But because this deployment army is there, it's a very costly process. You can imagine if we've got approximately 80 people spending almost a 24-hour period doing these deployments. When I walk in and say, you ought to be doing deployments once a week instead of once every quarter, they kind of look at me like I'm insane. Because given their context, it would be insane to say you should do this every week. But that high cost of deployment actually reinforces this whole cycle. The high cost of deployment means you do less frequent releases. And the less frequent the release is, the larger it's going to be, and therefore the riskier and more threatening it's going to be, creating more need for more humans. So you can see how this spiral works. Eventually, it produces paralysis. If you go around this loop often enough, you reach a point where you can't add any more people. You develop a playbook that's, an Excel spreadsheet printed out that thick. Eventually, you just hit the point where it's impossible to add any more to this process, and you feel like you can't take anything away from this process, and then you're stuck. I'm going to talk about what we can do about it. I'm not all, pessimism and gloom and doom. There are some solutions. But first, I want to look at why this situation comes about in the first place, why it persists, and why people perceive a conflict. Now, I'm a believer in the theory of constraints, and in the theory of constraints, there's this tool called the evaporating cloud. It's a great name. Your problems simply evaporate. The idea is that you try to identify the root cause of a conflict based on conflicting assumptions rather than real conflicting imperatives. And so the conflict we're going to look at here is achieving financial success in your company. Along one branch of this cloud, we have an idea that we want the benefits of being agile, and we want continuous integration all the way through to production. That's what we're here to talk about. That's what continuous delivery is all about. That's the cheerleading that we've done and we've heard about for quite some time. And that branch looks something like this. Financial success is produced by high velocity and short cycles, which means we need to do more deployments. But there's another branch of this cloud which says financial success is achieved by avoiding losses from downtime, bugs, problems with legal compliance, brand reputation loss, and so on. And along that branch of the financial success path, we see we need to reduce risk, which means we should be doing fewer deployments. Well, when we put these two branches together, we see the conflict. It looks like we have two things that we both need, or that we need both of them to produce financial success. I contend that this is not actually an inherent conflict. We don't need both more deployments and fewer deployments. We need to look at these assumptions about low risk and high risk. And so we're going to do that. When we talk about risk, some people use a very colloquial definition of risk. Risk means there's a chance that something bad is going to happen. Risk means I feel nervous or uncomfortable. Risk can even just be a scare word that you throw into a conversation, the way that some politicians like to throw it into conversations. Label something a risky scheme when you just don't want it to happen, but have no other argument against it. We're going to use a more nuanced definition of risk. We're going to say risk is the expected losses from undesirable events. And I mean expected losses in the statistical sense. If I do this trial enough times, I can average out the times that it goes badly and I lose something, and the times that it does not go badly and I don't lose anything. And so we reach this notion of expected losses, and we can look at that as our risk exposure. Risk exposure is often expressed in terms of the annual loss expectancy, or ALE. Annual loss expectancy is used in actuarial markets like life insurance and health insurance. It's used in security management for IT security as well. And to arrive at the loss expectancy, we basically run a small equation that says we have a number of events at which a loss could occur. We have a probability of any one of those events being erroneous, thus producing the loss. And we have a cost each time one of those events does occur. So the number of events times the probability times the cost, that gives us our expected losses. This is a useful definition of risk, because if we have expected losses in some kind of economic terms, then we can decide, first of all, how do we minimize it? And more crucially, is the loss actually greater than the gains that we could achieve by doing something else? Humans are very bad at economic decision-making on an intuitive basis, and we've had study after study that shows this. So we will tend to be loss-averse. If you ask someone whether they're going to bet a 50-50 chance on winning $1 million or hold on to $100,000, they'll hold on to what they've got rather than taking the chance, even though, mathematically, they should take the chance. So if you simply present the loss, people will try to avoid the loss every time. But if you present the loss and you present the gain available, then you have a chance of getting a rational decision after plenty of meetings and plenty of arguments and proof from other places and so on. Let's do an example of this kind of an exposure calculation. Let's suppose I'm running a retail site and I have some kind of a bug in my checkout process. I have a lot of checkouts per year, something like 10 to the 6th, 10 to the 8th. I can't actually read anymore. 10 to the 8th. So we have a lot of checkouts happening per year. But it's not a very common bug. It's something that occurs just once in a while. And so the odds of it occurring are small. We have a large number of events. And the cost of each of those events is basically whatever's in the cart. And we can say there's an average value of a shopping cart, call it perhaps 25 euro. And I can multiply all these together and say how much I should be willing to pay to fix this bug. How much am I going to lose on this particular bug per year? It works out to about 131 euro per year. So how much should I be willing to pay to fix this bug? Well, if the system's going to live for 1 year, I should be willing to pay only up to 131 euro to fix the bug. Otherwise, I'm paying more to fix the bug than I'm losing from the bug. If my system has a design life of 5 years, I should be willing to pay about 650 euro to fix the bug, because I'll save that much over the 5 years of the system. And if I have a 10-year life, and so on. You can work out the expected losses from this bug over time, and then balance that against what it costs to offset it. So this is an example of dealing with a small and relatively frequently occurring event. So these checkouts happen all the time. The cost of each one is relatively small. There are similar methods for dealing with the really large, horrible scenarios. So there are people who spend their time thinking about wonderful things like, what would it cost if an asteroid hit the Earth? I like to read these on the beach during the summertime. One book I can recommend is called Quantifying and Controlling Catastrophic Risks. The method is not dissimilar. The hard part is getting data, because we don't have a lot of asteroid impacts per year to measure and measure the cost of them. And we expect that when they do happen, it's going to be very expensive. The author of that one, John Garrick, also did a wonderful analysis on the actuarial impact of nuclear war. So maybe you'll want that for your summer beach reading. When we talk about risk and loss, we can start grouping the risk into a couple of categories. One of them is compliance risk. So this says there's some regulation or some law or some industry body, and if I'm non-compliant with it, they can levy fines against me. The other kind is the technical risk, more like the bug in checkout, where I'm producing the losses myself. Compliance risk is sort of tough to deal with. It tends to be industry specific, and if you're in one of these industries with a lot of regulation, you're probably dealing with approval bodies, third-party testing agencies, and the like, and there's a few things you can do. You can deliver into a certification environment, and you can deliver continuously into a certification environment and then get certified once a year, or whatever frequency that the certifying agency allows. You can make sure that you pass on your first time through the certification, but that's probably about all I can say on the compliance risk. It's simply a friction in your process that you have to deal with. I can say a lot more about the technical risk because that's much more under our control. And so that's where I'm going to spend the rest of the session focusing. When we're managing our technical risk, particularly related to delivery, we're going to think about our ALE equation and look at how each of these variables is affected by doing continuous delivery. So the number of events is going to increase. That's sort of a given. That's actually what we want to achieve. We want the number of events to go up. So we can work on decreasing the probability of an error and decreasing the cost when an error does occur. And that's where we need to focus. So I have a little comparison chart that we'll come back to and revisit a few times. We want to make sure that the decrease in the probability of error and the cost of an error is large enough to offset the increase in the number of events that we're going to be doing. And so let's look at where the probabilities of errors come from and see what we can do with it. Certainly defects in code are one of them. But that's not the only place you can get errors, because the code can all be fine and your unit tests can pass, but then when you put everything together and you push it out into the environment, maybe things don't work out there. So that would be an error in assembly. You left your development configs in the package that you put into production, and so you're trying to connect to a development database that's not accessible from the production environment. That would be an assembly or packaging error. You can also just have an error in executing the change. And when I was doing IT operations, this was the most common kind of error that occurred. We had something like 50% of all of our outages immediately following a change to production. Now, our changes were like the deployment army. So it was all manually executed. It was an administrator copying commands out of a playbook and pasting them into a terminal. And that's actually a good practice, the copy and paste. You know, every once in a while you pick up some smart quotes from Microsoft Word, but most of the time copy and paste is relatively safe because you can't typo something. You can't accidentally put in the wrong host name just out of finger memory habit. The defects in code are one of those things that accumulates over time. The longer you go between deployments, the longer you build up inventory, the more opportunities there are for defects, the more untested code you've got. And we can look at this with something like a continuous flow diagram. A continuous flow diagram comes from the lean school of process control. And basically, it looks at things entering a process and things exiting a process. But instead of counting sort of the number of things in process and having the wavy line like that, you simply add up one line every time something enters, and you add up another line every time something leaves. It looks something like this. What we can see here is the red line representing code that's been checked in. It's been you know, unit tested and feature complete, and it's done to your team's definition of done. It increases monotonically. We never subtract from it. It's continuous flow, so we keep going up. What we have on the black line is deployments. So nothing, 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 and then all at once there's a big deployment with a whack of code that goes out, and then nothing, nothing, nothing again for a while, and then another whack of code goes out. And the nice thing about a continuous flow diagram is that you can just look at the vertical distance between the two lines and say, that is my accumulated inventory. That's how much work in progress I've built up that hasn't exited yet. And I believe that accumulated inventory in code more or less linearly equals accumulated risk in code. So this is a diagram of a batch deployment or a punctuated deployment. If I take exactly the same flow of features, so the red line is going to remain the same, but I just move to a daily deployment following 1 day after the code is checked in, the CFD looks something like this. If you're in the back, you might not even be able to see the amount of accumulated risk between these two lines. I've done nothing else but change my deployment frequency so it more closely matches the frequency of checking things in, but I've dramatically reduced the amount of accumulated risk that's built into my pipeline at any point in time. This is the type of thing that we get with companies like Etsy and Flickr and SoundCloud and so on, who are doing continuous delivery and getting their code out there and validated in production as rapidly as possible. Because production truly is the only place you can validate all of your code. One way to achieve this is with the build pipeline idea. Some of you have probably seen this before. If you've read Jez's book, you've definitely seen this before. The notion of a build pipeline is you're essentially extending your continuous integration flow, which is this, and you're making that reach out all the way to your QA environment and eventually to your production environment, deploying as you go and applying tests for things like non-functional requirements in an automated fashion as you go through. And you tag your tree and you log and you measure at every step along the way, so when it fails, you can tell where it failed and why and go back and either fix the pipeline in about half the cases or fix your code in about half the cases. Now this is a fairly lengthy build pipeline and it looks a lot like what you would do manually. It's a good place to start by taking what your manual deployments would be and just translating them into an automated build pipeline. As you get better at this, you may add some stages or you may remove some stages. You may change the way that you're assembling. We can look at reducing our build and assembly errors by applying some practices. We certainly want fast tests so we get feedback right away. A very good practice for reducing build errors is building servers clean from a definition in version control. So using something like Chef, Puppet, or CF Engine so that you can commit all of your server definitions to version control and keep those in sync with the needs of your application. Definitely building the application from version control instead of building from a polluted dev box. Good practice. I hope everyone's doing that already. If not, that's an easy first step to begin. I still occasionally see environments where people are promoting sources and building on each target environment. This introduces a vector for change in that the target environment can have a different dependency set than your production environment or than the earlier environments where things have presumably worked. And so you don't really want different versions of libraries creeping in, different snapshots of jar files and that type of thing creeping in. So building binaries once and then promoting the binaries is a good practice. And certainly deploying the same way everywhere helps. I've seen a lot of situations where developers don't do a deployment on their own machine. They're just executing directly out of the directory that they're building in. And then they use something like Capistrano to deploy to a staging machine. And then they use a virtual machine snapshot and deployment to reach production. And so we're using 3 different mechanisms in 3 different environments that more or less maximizes the opportunity for assembly errors to creep in. So we don't want to do that. We want to build the same way and deploy the same way everywhere. I know I already said fast tests. Fast tests really are pretty important here. So I believe fast tests are an essential practice. Some shops continue to do feature work while the build is broken. I don't advocate that. I like to have a clean head of master. And if the head of master is not building correctly, you should not be committing new feature work. You should first get back to a green build and then continue feature work. You can commit feature work on branches, but first priority on master is fixing master. As you get more advanced with your builds, you can look at enforcing some of your architecture guidelines or standards in the build process itself. So one thing that we're taking an increasing look at is dependency management and the things that we're pulling in. It's been fairly common for us to have a developer pull in a jar file so he could use one function from one class, but then that jar file brings in all of its friends on the bus. So we end up with a stack of 40 jars, sometimes including entire other languages, just because we needed one thing. For example, I'm doing work in Clojure, and I discovered JRuby in its entirety existed in one of our projects because a transitive dependency included JRuby for its own interactive shell. Some organizations are very careful about what licenses they'll allow. And so this is another place where you can enforce license restrictions. If you have a separate development and operations group, it is really important to get operations involved in creating the deployment scripts. So that same company that I showed you the picture of at the beginning spent something like $1.5 million creating automated deployment scripts. The development group handed over the automated deployment scripts. The operations group said, well, that's great, but we don't like that tool. And so we're going to take those scripts and use them as specifications, and then we're going to write our own scripts in the tool that we like. So this is an enormous waste of money. And the odds of those two things, the 2 sets of scripts doing exactly the same thing, are pretty small. This could have been avoided had they gotten more buy-in from ops at the beginning of the effort and worked directly in the tool that ops was eventually going to support. And of course, if you haven't gotten the message about deploying from head of trunk, deploying from head of trunk is a really good approach. I favor feature branches as short-lived branches, but then reintegrate against trunk. Some of you may have seen this GitFlow article that talks about having a development branch and merging from master into development and deploying off of development. I've found that creates too many opportunities for error. People will merge things into development because they think, it's just development. But if you have a culture that says master is deployable, everyone will get that. In order to do these, there are a few things you're going to have to set up in your environment. I definitely think you need a package repository. You need someplace that you can put your binaries, that they can be safe, they can be checksummed, they can have version stamps, they won't get tampered with. You need logging, for sure. You need that for good operations anyway. And you need metrics to know if a change that you make is harmful and to know as rapidly as possible if it's harmful. And I'll be revisiting the subject of metrics in a little while. So that's packaging and assembly errors. The next kind of error that increases our probability of errors is deployment itself. And so let's look a little bit at ways to make deployments safe. Having 40 people working off of a playbook where there's a step that says, you know, we're going to call the DBA and tell the DBA to shut this off, and then we're going to call this other person and tell them to do that thing. That's sort of the opposite of making deployments safe. That kind of playbook evolves because someone really wants to be like NASA mission control. Actually, the best kind of deployment is one where you don't need a room full of people reporting to each other all the time. The deployment actually should be kind of invisible. Like nobody should even be able to tell when it happens except by looking at a graph. So there's a few patterns that you've heard mentioned today and that you've perhaps seen elsewhere. One of them is this notion of canary releasing. So in this pattern, you take a pool of your capacity and you make it the test pool or the dirty pool. And you deploy your new software to there and see how it does. It's called a canary from the old story of bringing a canary, coal miners bringing a canary down into the coal mine. Because if there was a buildup of carbon monoxide gas, the canary would die first before the miners. So the idea here is if something's wrong, the canary pool shows it first, and the users who are hitting the canary pool experience the problem first. So this is reducing the number of people exposed to a problem, but it doesn't actually eliminate the problem. You do have to assume that a certain number of errors are still going to get through here. So we're talking about reducing the probability of error, but we can't make it zero. Another approach is something that Jez has written about called blue-green deployments. This is where you have two pools of capacity. You split them up into arbitrarily named blue and green pools. You deploy your new code into one of the environments. You validate it. You can run some smoke tests. You want some monitoring and measurement on both pools. And then at some point, you switch over to using that. My favorite tool for using that is this really cool, high-tech name and dependency resolution service called DNS. At this point, green becomes your new staging environment, and it's the target of your next deployment. If you're in a cloud, this is obviously very easy to do. If you're not in any kind of a virtualized environment, it's going to be a little bit tougher because you do have to have some spare capacity laying around. Another style of making deployments safe is using a virtual machine-based deployment. So in this case, you have a server, not a dev machine, a dev workstation, but a server that's your dev environment. And at some point you say, yes, this is good, I bless it, and you create a virtual machine based on that image, and then you use that virtual machine to deploy into your higher environments. The key advantage here is there's very little opportunity for errors to creep in during the deployment because you're not changing the essential machine as you move through environments. The next approach you can use for making deployments very safe and predictable is configuration management-based deployments. So in this scenario, I've split up my capacity into the control plane, which manages the infrastructure, and the service plane, which actually does the work. Not a lot of work is going to get done yet in this picture. But at some point, I have a base image. In the previous slide, I was showing you a fully configured application in that virtual machine. In this slide, I've got just the operating system plus a configuration management client. It knows how to talk to that config server, and that's about it. So that basic machine gets instantiated in the service plane. And the first thing it does is it talks to the config server and asks, who am I? This is how Chef and Puppet work. CF Engine also works this way. So the machine asks, who am I? What's my role? What are my configurations? It downloads those configurations, pulls packages from your package repository or from the config server, and starts installing things on itself. If all of that succeeds, it begins reporting its metrics to your metrics server, and at some point, it also needs to report its versions of everything back to the config server. And it's really important to close the loop here because kind of a common failure mode is one of your machines doesn't get updated, and so it's actually running old versions of stuff. This is a really weird problem to detect in production. And so it's good to build a page into each of your apps that reports the version that it's running, and then collect all of those on your config server so you can look at a simple report and immediately identify anyone that's running an old version of the software. And then you blow that machine away and start up a new one in its place. Now, in order to do any of these things that I've just talked about, you do have to put in place some kind of a zero downtime deployment mechanism. Because at some point in time, you're going to have the new version of your system and the old version of your system alive together. So it's important to do this in a structured way so that you can handle things like database migrations. And you can split up your database migrations into a sequence of safe steps so that you're doing additive operations first, you get all of your code rolled out, and then you do the subtractive or restrictive operations. So first you add tables and you add columns with one small change, then you push out your code with another small change, and then once you're satisfied that everything's working, you push out another change that leaves the code alone, but drops tables that you don't need anymore, drops columns that you don't need anymore, adds any not null constraints that you might want to apply at that point. And so you do these in phases. As you do this, it is very important that you think about how the different applications and services are going to know each other's protocols as well. So maybe you just build all of your applications to always speak every version of every protocol they've ever spoken. You could do that. Might be kind of a costly approach. You can build protocols that are forward compatible, so they ignore any unexpected elements. This is a good approach. And you can do it by explicitly negotiating what protocol versions you're going to accept. Think about something like HTTP content negotiation, where you have custom media types that represent versioned formats of your representations. And then you can say, I accept version 1 and 1.1 and 1.2. And then the server says, I'm happy to give you 1.2, but I'm not going to give you 1.1 or 1. I don't do that anymore. Another very key issue with zero downtime deployments is a decoupled architecture. I'm going to talk about this more a little bit later. So I contend if we do these things, pick a safe deployment mechanism, pick a safe assembly mechanism, create a build pipeline that gives you visibility, you can actually reduce the probability of error to something quite low. But what can we do about the cost of an event? By an event, I mean, some kind of a downtime or crash or bad user experience. This is where it gets kind of interesting when you talk to people who don't have a kind of quantitative risk approach, because they start to talk about all kinds of scenarios. And you see this weird sort of glee in their eyes as they're talking about getting on the front page of the newspaper and getting called in front of your legislative body to testify about why they leaked everyone's credit card numbers or health information or this kind of thing. And they have this sort of, apocalyptic joy as they're talking about these things. I had a boss in a past job who referred to this as the wouldn't it be horrible if scenarios, or the WIBIHEs. People love to talk about WIBIHEs in the same way they love to talk about movie plot threats. Of course, it's not a rational approach. If you're engaging in WIBIHEs, then the cost of any event is unbounded, right? Because you can't imagine a limit to how bad things could get. And of course, if the cost of an event is unbounded, then the things you should do to prevent it is essentially unbounded. And you're going to end up with 80 people in the conference room and on the phone doing deployments for 24 hours. The real cost of an event is, it is bounded. It is limited. It adds up from several factors. You have direct losses, so revenue and cost incurred during the event. You have some indirect losses. Loss of brand reputation is an indirect loss. The cost of people's labor while they're responding to the event instead of building the next great thing, that's a loss. But we can add all these up, we can measure them, and we can work to minimize them. So let's look at how we do that. The first and best way to minimize the cost of an event is just to minimize the time to detect it. So MTTD is the mean time to detect the event, and it's shockingly high in many cases. So I've seen systems where people are running synthetic transactions. So you have some service that you've signed up with that runs load against your site, and they run a transaction once every 5 minutes. But that transaction they're running goes through a load balancer, and it gets directed to one of n machines that you've got. So the first time suppose you've put out one bad server out of a pool. The first time that synthetic transaction happens, they might not hit the bad server. And actually, once they eventually do hit the bad server, they usually retry a couple of times before they say, yes, it's a real problem, not just a transient network issue or a failure to resolve DNS or something like that. And so with synthetic monitoring, your mean time to detect is usually on the order of 15 minutes or more. That's kind of long in systems that I deal with. If you're using something like real user monitoring, where you're watching traffic coming in from outside, and you're watching the effects of that traffic, you can usually see the event in a minute or less. So real user monitoring gives you better mean time to detect. We can talk about different testing methods and see what the mean time to detect a problem with the different testing methods is. So I do unit testing. I think it's a big advance in our profession. But I have to say, I don't get a lot of confidence in the validity of my system just based on unit tests. It tells me a certain amount, but it doesn't tell me it's actually going to work in production. So I have relatively low confidence in its validity. But it's very fast to detect things. So unit tests have some utility. Integration tests take quite a bit longer to run. Right? I can usually run unit tests in a matter of seconds. My integration tests take a few minutes to half an hour or something like that. They do give me more confidence in the outcome. Sometimes we do this user acceptance testing, where we actually put the system in front of some of the sponsors or stakeholders, and they're supposed to be the final step in approval to make sure it actually works. That takes a very long time, and I don't think it actually adds much confidence. What I normally see in user acceptance testing is a very cursory sort of, click, click, glance at a few pages, yeah, it's okay. I don't see, real in-depth exhaustive testing. A method that does give pretty good results is this real user monitoring. And so I definitely advocate measuring everything your users are doing, charting it, and find the charts that matter for your environment and your business. Mike Britton is going to be doing a talk a little bit later. He comes from a company called Etsy that has blogged about their cult of charts. And so I've borrowed, with attribution, some of their sample charts. So this is a chart showing technical metrics. And just at a glance, you can see that something very odd happened immediately after a code deploy, and the number of PHP warnings went way up. Another code deploy went out, and the warnings went way back down. This is a great example of detecting a problem and correcting it pretty rapidly. So I would wager that the time to detect was on the order of 5 to 10 minutes, and the time to correct was 5 to 10 minutes. This chart will show you problems before anyone in a call center will get a call, And actually, way before synthetic transaction monitoring will show you a problem. Here's another chart that they've got. This one shows some metrics that are perhaps more of interest on the business side as well. And again, you can very clearly see something odd going on in the middle of the night there. And so this kind of visibility shows you errors faster than anything else. It's very easy to set up charting and chart everything. You take your server with your stack of stuff, you add some open source software like StatsD, you do a little bit of internal monitoring, you send it all to Graphite, and then you can get out your dashboards and charts and information radiators on the wall, and everyone starts looking at those things. There is one caution, which is the first time you make something visible, it will probably look horrible. Because if you haven't looked at it before, weird things will have crept in. And this probably means that your higher-ups are going to look at it and go, that looks really strange. Please explain that to me. And so you'll get asked to explain a lot of things. That goes away quickly. Don't let that scare you away from doing this. You can blend in external monitoring with this and feed it into the same system. And everything that I've represented here is approximately a day's worth of work. So it's really easy to get going with this stuff. The next step in minimizing the cost of an event is reducing the time to correct it, or the mean time to recovery. If you're looking at mean time to recovery, it comes from a few places. First, you have to figure out what's going on. Sometimes that's the fastest part. You look at it and you instantly know what's happening. No orders are being placed. Sometimes it takes a while longer. I've had time to determine the problem measured in weeks in some cases, but fortunately that was a very intermittent problem. It wasn't a huge crisis issue. Certainly fixing the problem and deploying a fix are parts of the mean time to recover as well. So being able to make the change quickly and get the change deployed quickly help you reduce the cost of the event. I think an area that we don't look at enough is how to reduce the scope of an event. Now you remember when I talked about the canary pool, I said that the users that you have hitting the canary pool are the ones experiencing the problem. Well, that's a small fraction of your users, so you can regard that as kind of the scope of that event if something bad happens there. So we can ask how many users are going to see the error. Split testing like the canary pool or just A/B testing features is one way to reduce the scope of the error. We can also reduce the scope of the error with a dark launch where the only people being exposed to the problem are sort of our own people and friends and family. People within our circle of trust, I guess. Feature flags are a way to reduce the scope of the error as well. So you can turn it on a limited number of machines, and if something's going wrong, you can turn it off on the same machines very quickly. I always like to have some kind of a remote control mechanism built into my systems. I don't want to have a bunch of admins scrambling to SSH into 20 or 30 different boxes and try and make the same exact change to 20 or 30 different boxes. Because they'll get it wrong in at least one of those. And it just takes time. The first box will get fixed fairly quickly. By the time they get to the 30th box, 5 or 10 or 15 minutes have gone by. I like something instead where I can drop a message in a queue and have all the apps in my infrastructure reading from the queue and doing the thing to themselves that the message tells them to do. Whether it's turning a flag on and off, whether it's accepting load or shutting off and shedding load. Another aspect of the scope is how far does the error go? So if I have an error, is it confined to a single feature? Or is it affecting all of my features simultaneously? And this is where we come back to the notion of the decoupled architecture. We can use bulkheads to separate different pools of servers. So if I've got some kind of a distributed bug that's causing machines to lock each other up, I can have different groups that are incapable of locking each other up. And I can use circuit breakers to prevent errors from jumping gaps in the system across vertical tiers and propagating outward into, from service provider to service caller. So a couple of examples of what this decoupled architecture would look like. This comes from an actual client project. Essentially, they had one big app. There were multiple teams working on the independent components. Each of the teams would check their code in, and each of the team's code was being built into a module, but then the modules were all being glommed together in a single big jar file. Actually, I think it was an ear file, but effectively it's a jar full of jars. And then that same file was being deployed to every app server in parallel, and they would all get restarted. Well, this is the opposite of a decoupled architecture. We can make it a little better by doing the canary releasing and saying I've got a little bit of my capacity that's now my canary pool. And I'm still kind of assembling things the same way. But in this case, at the very least, I can reduce the scope of who all is affected by this. And so this is better. It's still not great, but this is an easy step to make. And so if you're still in that kind of monolithic, doomed scenario, take this step and then move on to the next step, which looks like this. We've now taken the modules apart into groups of related facilities, and they're each being deployed to their own pool of servers. At this point, I can have any kind of hairy threading bug in my account management. I can have this thing calling through to some back-end system that exhausts its thread pool and never answers again. And the worst that happens is that I lose those account management features. But I don't also simultaneously lose all the threads that respond to all the other features. Now, one other advantage of doing it this way, by the way, as I depict over here on the right, is now that the communication is not straight from the user to each of these facilities, I can also start saying individual facilities have their own canary pool, and I can validate those and then turn them on for a fraction. So I can make multiple versions of these services coexist, either for a limited time or for an extended time if I want to do protocol versioning in an easy way. Now, one of the interesting things is when we talk about decoupled architectures, one particular group of developers gets very high marks on the decoupled architecture that we tend not to give very high marks anywhere else, and that's the PHP developers. Because their code is so UI focused and it doesn't tend to get packaged up into these artifacts within artifacts within artifacts with this stack of dependencies, it's relatively easy to just push out a few files with a few lines of changes. There's not an issue of restarting whole app servers with 25 megabyte jar files. So I think we have to cut the PHP developers some slack or give them some credit on the decoupled architecture area. So if we've done these things, I contend that we have reduced the cost of an event and we've made it quite low. And I believe when we reduce the probability of the error and we reduce the cost of the event, we have a squared effect going on. So we're increasing an events linearly, but we're reducing the probability and the cost by a squared effect. And so that should win, which means if we do these things, then the risk of doing continuous delivery is lower than the risk of doing batch delivery. So this is the motivation behind a lot of the practices that we've been talking about earlier today, that we'll talk about through the rest of today, and that we've talked about in previous iterations of this track. There are some unsolved problems that I'll mention very briefly. These are areas where we're looking for contributions. We're looking for people to figure out the innovation that will solve these problems. One of the big ones is library dependencies. So if you're using some kind of a build tool that pulls in libraries from random places around the net, like Maven Central, you have a risk exposure to anything happening with Maven Central. I work in Clojure, and it's common to use this service called Clojars for Clojure jars. Clojars has no authentication, that you are actually the owner of a project. You can claim any project you like and start uploading code. This, to me, feels pretty risky. So we don't want to just depend on all the random libraries out there. We probably want to run our own repositories with the libraries that we trust. But now, of course, we've got to manage that repository of libraries and keep it up to date. So I regard this as an unsolved problem. Service and protocol dependencies, we've got some answers. None of the answers are perfect. So still more to do there. And if anyone's in an organization where you're dealing with ITIL processes, there's nothing in the definition of ITIL that's incompatible with continuous delivery, but the implementation of ITIL in many organizations is incompatible with continuous delivery. So this is also an unsolved problem. If you are in such an organization, I'd love to talk to you at some point later on today. So with that, I'll leave you with a few questions to think about. Ask yourself, how would you do things differently if you could rebuild your environments this way? If you're not doing this already, I've given you many different small steps you can take and some large goals to aim at. Think about the smallest change that you could make that would take you one step of the way there. And then think a second time, because usually when we try and think of the smallest change, we actually think of something way bigger than the smallest possible change. And if there are manual things that you're doing, just find one thing that you can automate and move in that direction. I'm sure there's at least one thing that you could automate that you just haven't done so far. And organizational barriers are going to be there. We heard from Josh about the people changes and the culture changes. So think about ways that you can begin to initiate some of those changes. And it usually doesn't start by telling someone else that they need to change. That's an anti-pattern. So finally, I just want to say that we should not support or allow this type of thing to happen anymore. If you have a deployment army in your company someplace, send these people home. It's a waste of time, it's a waste of resources, it's a waste of humanity to do something that computers could do. We can do way better than this. And so let's let these people get some sleep, because it looks like it's about 1 in the morning there. Thank you.